Hi everyone.
Okay.
He's going to use them for it.
Let's start.
Hi everyone. Thanks for coming today. Today, Guido is going to talk about the Unruh effect and do a nice whiteboard style talk. Grab snacks now or forever. Hold your peace in bag rustling. Yeah.
All right, so this is going to be a very short presentation of this effect due to the time, but hopefully I'm going to try to cover all the main steps to derive this. So this effect is timely put in the context of quantum field theory in curved background, even if it's really on flat Minkowski spacetime. But the machinery and the tools that are used to derive this effect are basically very similar. So what basically this effect is saying is that, let's suppose I'm an inertial observer in Minkowski spacetime, so I'm sitting here still, and then in my system I have a quantum field, and let's say I have a detector in my hand, so I can measure the excitations or the particles associated to this field. So in my inertial frame, I pick up my detector and I look 0 particles. Like my detector is not clicking, it's not measuring anything. And so I say, okay, from my point of view then, I conclude that what I'm seeing is the vacuum state, so the lower energy state of the field. But then now, let's suppose that an accelerated observer with constant acceleration with respect to my frame is flying through this room and is looking at the same quantum state. Now, he's also carrying a detector in his hands. What will his detector measure? Now, his detector is not measuring 0 anymore. Actually, he's measuring some thermal distribution of particles. And if the detector can measure the energy of each particle that it counts, it can basically reproduce a black body radiation at a certain temperature that is called the Unruh temperature. And this temperature depends on the acceleration that this observer has with respect to the inertial one. All right, so first of all, I want to just briefly recall all the canonical quantization of the classical field theory, just that everybody is on the same page in this. So we basically consider just a real scalar field because it's the easiest example that we can discuss, basically, and we would derive this effect for just a free real scalar field. So ideally, we can start like this conceptual picture just by starting with standard quantum mechanics. So in standard quantum mechanics, we describe a particle from some classical variables, the canonical variables, like the position and momentum. And then we basically quantize these variables by promoting them to operators. And then, of course, we will have some equation of motions. There are the Hamilton equation of motions, which can be rewritten in terms of Poisson brackets also. And then the corresponding principle in standard quantum mechanics promotes basically these Poisson brackets to be commutators of the operators. So we have something like. So from now on, just for simplicity, I'm going to assume relativistic units. So h bar equals c equals 1. So you don't have to carry these things around. And then these operators are acting on a Hilbert space. And this Hilbert space, like the states of this Hilbert space, the evolution in time is governed by the Schrodinger's equation. So I have some equation for my quantum states that evolves in this way. Now, the jump when we do relativistic quantum mechanics is that we ideally, at first at least, we want to generalize this equation to be a relativistically invariant equation, at least under the Lorentz group or the Poincare group, because this one is not. And so the first idea of generalizing this is the Klein-Gordon equation, which is simply box plus m squared of some field equals 0. Now this box in an inertial frame is simply the alpha, which is just a standard wave operator that you all know. So the solutions of this equation are then just plane waves, because this one is just a simple wave equation. Now from now on also I'm going to assume massless fields, also for simplicity, but the derivation can also be done for massive fields as well. Now, as I said, you can basically form a basis of solution of this equation that is formed by all the plane waves for all the Fourier modes, basically. So we can solve this in terms of some u, that is e to the I omega t, and then e to the I kx, which solves this equation. And if you plug in this into the Klein-Gordon equation, what you get out in terms of the dispersion relation that connects the frequency to the wave vectors, what you get is, it's basically that omega can be either plus or minus k. Also here I'm assuming just a 2D spacetime just for simplicity, so I just have one single time coordinate and time coordinate and a single space coordinate. Now, where is the problem here? The problem is that I have some solutions that have negative energy, so negative frequency, which means negative energy. The problem is that I cannot discard them if I interpret this field phi as a wave function, because I want to build the complete basis of my Hilbert space. So I cannot say get rid of this. So then this, together with another problem that I'm not going to discuss, basically said, okay, we cannot construct a relativistic field theory, a relativistic quantum mechanics theory that is based on a single particle. We have to change our classical theory that we start from, and then we quantize it. So the trick here is basically considering no longer as your classical fundamental variables the ones that describe a single particle, but consider the field itself as your classical variable to quantize. So pretty much as you have like field equations in electromagnetism, here we're going to consider our classical field equations directly the Klein-Gordon equation. So we are no longer interpreting this phi as the wave function, but just a simple classical scalar field. So by doing that, we can, so instead of having this now, we consider this as our base point. So we have this wave equation. Now for the massless case, it's just this. And to quantize in the similar way, so to promote the field as an operator, we want to promote this, basically this Hamiltonian form into operators and computational relationships. So the way this is done is simply by defining an auxiliary variable, pi, which is just a time derivative of phi, and then as a consequence, the time derivative of pi is going to be reading off from the Klein-Gordon operator, is just going to be the second derivative of phi. This is just Klein-Gordon equation split in like in first order derivatives. So you can see that this is formally the same as like the Hamilton equation for Q and P. Whatever Hamiltonian is saying here, 0 in the case of the free field, free particle. And so we can interpret this pi and phi as the canonical variables like Q and P. So in this case, then we're going to promote this pi and phi to quantum operators. And then we're going to have a similar relation in terms of Poisson brackets for these classical fields, which is going to be something like this. Now, instead of having one here, now we have a direct delta function because we have infinite many modes in the spatial components. So this is basically accounting for this. And so at this point, we can generalize this to some commutation rules between our new quantum operators in a similar way as we did in this case. So here just we have this direct delta function is basically doing the same thing as the one here. All right, so this is basically it. We quantized a field, and now we have a relativistic quantum field theory. But why this solved our initial problem of negative energies? Well, if we expand even just the classical solution of our Klein-Gordon equation, so we write the general solution in terms of these basis functions that we derived here, this is in general is going to be some linear combination of all these possible modes. So some uk of dx times some coefficient, and then since my scalar field I want to be real, also the complex conjugates of this quantity. So u star k dx ak, where here I'm just taking the positive frequency now, so the negative frequency modes are just the complex conjugates here. Now when I quantize this expression, so I promote these guys as operators, these coefficients get also promoted as operators, as a conjugate, get also promoted as operators, and this conjugate now is becoming an Hermitian conjugate. And the cool trick is that now I can know what is the Hilbert space upon which this operator is acting on. Because if I impose these commutational relationships on this expansion, so I take this and I plug in here, then I take the time derivative to get pi of this and I plug in here, what I get is a commutational relation for the AK and the A dagger. So I will get something like provided that I normalize this thing accordingly with some normalization factor that is basically 1 over 2 omega squared. But now we solve the problem because for each mode k, we know what is the Hilbert space of the quantum harmonic oscillator. So the Hilbert space for each mode k is going to be spanned by all the number states, basically, that we all know from the normal quantum harmonic oscillator. So we're going to have all the possible number states. And we know that we can create or destroy these number states using this algebra of creation and annihilation operators. So in particular, the annihilation operators kills the vacuum, and then if I have a number state with n excitations, this is basically gonna reduce by 1, and instead the creation operator is going to add 1 excitation mode. And now the energies are also positive, because each of these states has the energy of a level of the harmonic oscillator, which is strictly positive. So we have that, for example, the energy of the n state is going to be omega n plus 1/2, which is strictly positive. So now we have constructed a Hilbert space that is perfectly fine, and it's relativistically compatible. One final thing that I want to define, so we associate now the concept of particles as these number states, basically. And then we construct, finally, our full Fock space as by taking just the product for all the modes of this Hilbert space. So this is going to be just a big tensor product of all the possible Fourier modes. Now, finally, the last tool that I want to just recall is the number operator, which is just A dagger A. And this, if you follow the commutation algebra of this object, is basically just extracting how many, like all these number states are eigenstates of this operator. So if I do, for example, this, I get back as the eigenvalue the number of particles in this state. And so if I compute the expectation value of a number state over this number operator, I just get the number of particles that I have. So for the vacuum state, I will get 0, of course. Okay, so this is the rough, just quick presentation of quantum mechanics. And so now we can jump to something more interesting. So first of all, this whole construction was possible because we were in an inertial frame. So we had some nice coordinates, t and x, over which this box operator is in this nice separate form, and we can define these states of positive and negative frequencies with this time coordinate here. But in general, for general spacetime, this is not always possible. So I want to just briefly touch when it's possible. So let's suppose we have a general metric, or this would also be Minkowski metric in some arbitrary coordinate system. If you do have that, the Klein-Gordon equation, which in general, as we saw before in an inertial frame, it's something like this, will be generalized with the partial derivatives becoming covariant derivatives now. Where here I can just drop the innermost one because it's acting on a scalar field. And now, of course, this equation will be more complicated than the first one, because I have Christoffel symbols, gonna have like a complicated metric, and so on. So the solutions won't be these plane waves, nice plane waves anymore, and so I cannot construct all this thing again. So the reasoning behind this then is that I can still do this if I have a time translation symmetry in my spacetime. So my spacetime is stationary. So it exists basically a time-like Killing vector. So it satisfies Killing equation. So we know that if we adapt a coordinate system along these Killing observers, so this time-like Killing vector field can represent the 4 velocities of these observers, then we can basically get out of the Killing equation that dt g alpha beta is equal to 0, which is just the stationarity of the metric, like Schwarzschild metric in Schwarzschild coordinates or Minkowski metric in inertial frames. And then we can define also some orthogonal space-like coordinates to complete our reference frame. In that case, here will also be cross components of the metric. If you do that, you can basically rewrite the Klein-Gordon equation in a much simpler form in this frame. And you will basically assume if you open up this, you open up the Christophels, and you put in these assumptions, what you will get is basically that the Klein-Gordon equation will look something in general like this. So once again, we have separation of the variables in time and space, and so you can again solve into some solutions that have the e to the I omega t, and then some spatial solution that in general will be more complicated than a plane wave, because this depends on the shape of this guy over here. But this is basically the trick. So from now on, we're going to always consider Killing observers. So observers that, like coordinate systems that are constructed with a time Killing vector field. All right, so now let's get to the actual meat of this whole thing, which is the Bogoliubov transformations. So let's suppose we have two frames, okay? So two coordinate systems. So we have one observer with one coordinate system, and then a second one. So as I said, the Klein-Gordon equation can be expressed in this coordinate system, and it can be different. It can have different set of solutions, right? So let's call the first set of solutions as UK star. So this is like positive and negative frequencies. And then I have a new set of solutions for this second observer. There will be some VK tilde and then VK tilde star. Of course, each of these observers will carry over the canonical quantization and will split the field into this infinite set of our harmonic oscillators once again. So with his own creation and annihilation operators. So we're going to have here a dagger K and a K. But now this guy will have a different split of our field into a different basis function. So we'll have some creation and annihilation operators that in general are different. So what I mean is that we have a scalar field that is an invariant, doesn't change under these coordinate transformations, but we can express it with the first frame as we did before in terms of this complete basis, which is just the expansion that I wrote before, or the same field we can express it in terms of the second observer, in terms of its own basis. In this case, I'm going to use phi. So now here's the trick. We know that the Klein-Gordon equation is a linear equation. So if we have two sets of solutions, they have to be linked by a linear transformation between them. So these are like two sets of solutions in the Hilbert space of the solutions. So in general, we can say that UK can be expressed as a linear combination of the other bases, basically.
Sir,
Yeah.
sir, are you dealing with flat spacetime or with the general spacetime?
This description could also be in general spacetime, with the only caveat of having a time-like Killing vector field as like the d by dt of our coordinates.
Okay, but in general spacetime, the Klein-Gordon equation is no longer linear equations anymore.
Well, it's always linear in phi though.
Okay.
This is what I mean.
Okay.
We want to have like phi terms or like stuff like that. So you can have second order derivatives, that's fine. But in general, like it's always linear in phi. So the solution space, you can always express one of the solutions in terms of linear combination of all the other bases, basically.
And
as long as it's complete.
And both of the two observers are traveling along the Killing vectors?
Yes, but they're in general they could be two different Killing vector
Okay,
fields,
I see.
right? So this is important. So in general, like you can express this as a linear combination, and of course here we are dealing with like continuous indices. So linear combination means not summing but like integrating. So we're gonna have some integral in the k tilde, and then we have a bunch of coefficients. So for example, we can call this star k tilde k. Just don't mind to the star. It's just a definition, like convention. And then we have v k tilde, and then generally a different coefficient times v k tilde star. And then of course you can do the same for u star in terms of the other guys. So this is called the Bogoliubov transformation. It's very general. as a statement. But now we see that if this is the case, then if you want to recover the same scalar field with these combinations, the creation and annihilation operators B and A must also transform in this way to compensate for this change in the basis. So you will get basically a very similar transformation for example, for BK tilde. It's going to be something similar. You can just take this and plug it into the expression and read off how the B and A's are related, basically. And so what you will get, if you do the calculations, is something like this. So this is the second important relation of Bogoliubov transformations. And this is what it's saying is that the new observer can express his own creation or annihilation operator in terms of a linear combination of the creation and annihilation of the story. there's a should be an A. So yeah, indeed. The second observer
told us on the A's, right?
Yes, thank you. So this is good, this is not good, this is not good, and this is good. Yes, thank you. So yeah, the second observer can express his creation and annihilation operators in terms of a linear combination of both the creation and annihilation operators of the first observer. Now, this is a non-trivial statement because now we're going to see that, I mean, you can already see how this thing is going, where this thing is going. But if we have a different set of B's and A's that are not one-to-one related, then the vacuum state will be different because I will have a vacuum for the observer 1 that will be annihilated by A, and then I will have a vacuum for the state for the observer B, for the observer 2. That in general is different because these two guys are different, right? So one more thing is that these A and B coefficients are not independent from each other, but if you impose that these transformations preserve the commutation algebra, so the relationships that I defined here between these guys, and so you impose that it's also true for the B's now. What you get is that you basically get something like, just schematically, to some delta. So if this guy is 0, then you basically get that B is equal to A, essentially. Okay. So we can basically quantify how much we have this mixing by basically computing this beta coefficient here, which is also called like Bogoliubov coefficient. So you can also see this, why this beta coefficient is important, because if you compute, once again, the number operator, let's say with the new observer, so this is going to be B dagger K tilde, BK tilde, and you compute now the expectation value of the vacuum of the first observer as seen by the second observer. So by definition this, which is exactly what I was saying at the very beginning. So I have a vacuum state seen by the inertial observer, which in this case is the observer 1, for example. And then as an accelerated observer, looks into the same state, measures with his own measuring tools, and he measures something. So this is exactly what I'm saying. So observer 1 in the Unruh effect case is the inertial observer, observer 2 is the accelerated one. So if I carry out this computation, so this is again BK tilde dagger BK tilde, and I use the Bogoliubov transformation, I substitute it inside, I will have like 4 terms, and I then use the fact that AK, when it sees the vacuum, it gets 0, so we'll be left with just 1 term there, and this will be simply the norm of this beta coefficient. So this is actually exactly the number of particles that the second observer sees on the first observer vacuum. So at the end, like the entire computation of the Unruh effect is basically calculating this gap. Okay, so to conclude this discussion about Bogoliubov transformations, I want to quickly say why you haven't seen these things in a quantum field theory class. probably. Because when you're within the Lorentz group, and actually to be correct, the proper orthogonal Lorentz group, so no inversion of time, then this beta coefficient is 0 if you jump from one inertial observer to another inertial observer. So you don't have to deal with this thing. And the reason why this is the case is that if I pick, for example, so as observer 1, I have a basis of solution that will look like e to the I omega t, e to the I kx, as said before, or if you want in more relativistic notation, you can write it this way. Then the observer 2, like the second inertial observer, let's call it V for now, will have the same solution right here, because the Klein-Gordon equation doesn't change if you jump from one inertial observer to the other. It will be exactly the same form. So you will have e to the I k mu tilde x prime mu. And we know that from the coordinate transformation between x prime and x mu for Lorentz transformation is this. So basically you can, in this exponential here, you can move this action from the coordinates to the k vector. So you can have a lambda mu nu k tilde mu x nu. And so you can redefine basically the wave vector to a new one, let's say k tilde prime nu. And so what you get out from here is that you get exactly the same form as here. So this is exactly u for a different index here, gonna be k tilde of dx. But remember, this is of t prime x prime. So these are exactly the same solutions. We only just rescaled the wave vector, but the wave vector, when you expand the field, is always summed over. It's a dummy index. Doesn't really matter. The only thing that matters here is the sign of the temporal component of this guy. Because if it's flipped, then we might have problems. But for a proper orthogonal Lorentz transformation, this doesn't happen. So the time direction is not flipped by this. It's just rotated a little bit in Minkowski spacetime. So this is fine. We don't have to deal with these guys. We can simply express this as basically the other. They're the same. So no mixing between positive and negative frequencies. All right. So this is basically what I wanted to say about these Bogoliubov transformations. And now that we have this whole setup, we can discuss. Yes?
Why isn't the number of operators of the observer 2 acting on the vacuum that is seen by the observer 2 as well? Why is it? Why is it acting on the vacuum that is seen by the observer 1? I think I'm kind of confused here.
You mean, okay, so...
If these two vacuums are not different.
Yes.
Are not
so,
the same. Yeah.
Yes. So we prepare our system in a single quantum state, right? And then different observers see on the same vacuum state different things, basically. So, but the state of the system is one, basically. But different observers will look different things into it, basically.
The different observers have different sets of operators.
Yeah.
Described.
Yeah, but then why do we have to kind of distinguish the two vacuum here now that they are actually measuring the same vacuum state?
No, so for him, this is no longer a vacuum state. Because the particle numbers that it measures is not 0 anymore. So this would be, again, a vacuum state for the second guy if this is 0.
Also, the vacuum state that seems like a state that seems like a vacuum state for observer 1 is not a vacuum state.
Exactly,
for
yes.
Okay.
Yes, correct. Yeah, so any other questions about these things? Okay, good. So now the program then to compute the Unruh radiation, it's basically the following. So we need first to define some suitable coordinates for the accelerated observer. So define so-called Rindler coordinates. Then once we have the coordinates, we need to write Klein-Gordon equation in these coordinates and solve for a basis of solutions in these coordinates. So solve Klein-Gordon equation in Rindler. And then third, once we have the solution, we can build our different field expansions and we can compute the Bogoliubov coefficients. And this will lead us to the final result, basically. So compute. Okay, so the next step in this program, should I move this way for the camera? No, okay, it's fine. It's going to be defining what a Rindler observer is, or what an accelerated observer in Minkowski spacetime looks like. So, say Rindler coordinates. So now we switch back to just basic special relativity in some weird coordinate frame. So we want to start from an observer that has some word line that is parameterized by its proper time, and this word line is expressed in terms of some inertial coordinates, so inertial frame. So this is going to be some t of tau, oops, x of tau, and then we're going to ask that is for acceleration has a constant norm, basically. So a mu is equal to minus a squared. This minus is coming for the signature that I chose, which is like plus minus. So this guy is constant. And this is the only parameter that we have in our model, basically, so far, because mass is 0, and so this it just depends on a. So now you can rewrite this guy, you can plug in this in here, and what you get is basically an ODE to solve, a second order ODE. So you can solve it, assuming some initial conditions. So usually the initial conditions are that the forward velocity of this observer at 0 proper time is 0. So it starts still at 0 proper time. And then the position at t equals 0, tau equals 0, is such that this is going to be 0. So the coordinate time coincides with the proper time, and then the position is defined as 1 over a. This is just for convenience. This is nothing crucial. So if we draw this word line with respect to the inertial observer in Minkowski spacetime, so some x and t coordinates, I have a light cone over here, 45 degrees. This observer starts from the x-axis at 1 over a, and then you can recognize that if you solve these equations, you will get an hyperbola. So you can basically see that t of tau is equal to 1 over a hyperbolic sine of tau a, and then x of tau is 1 over a hyperbolic cosine of tau a, which is the parameterization of an hyperbola. So this is good. This is how it's the hyperbola is like the observer is moving forward in time, and you can see that like if you want to solve the same problem in Newtonian mechanics, you would have a parabola in spacetime, like 1/2 a t squared. And this is very similar, close to here, basically. But as the speed increases, special relativity tells us that we cannot go at infinite speed. And so eventually the speed has to approach the speed of light here, which is what is happening in this case for this word line. Now this is not a coordinate system, this is just a single observer. So ideally we need to extend this to a family of accelerated observer with constant acceleration. So ideally the picture would look something like another hyperbola here, then I displace it again and I see something like here, then something like here, something like here, and so on. Of course, I cannot just displace them because they have to still be inside this light cone. So I also to add more and more acceleration as I push this hyperbola closer and closer to the light cone, basically. So to achieve this is actually pretty simple. I can simply call sort of like this displacement as chi, or c, a new coordinate. And so basically my family now will look like this. And so now I have a coordinate transformation because I have some inertial coordinates, dx, and then I can define new coordinates as xi and tau. So this is my coordinate transformation. And you can see that these coordinates, like these coordinates cover the entire spacetime, but these do not. Because the range of these coordinates is actually c goes from -1a to plus infinity, and tau goes from minus infinity to plus infinity. It goes to -1a because the coordinate transformation becomes singular at that point. So we are basically, if you are looking at some word lines with a c that is -1a, we are exactly at the light cone. Instead, if you push it c here, you can push it indefinitely and you're fine. This coordinate tau instead, it's fine, can span from -infinity to future infinity. And in this case, if you plot the constant tau coordinate lines with respect to the inertial observers, it will look like just straight lines in this way. So these are Rindler coordinates. So we parameterize this wedge, this right wedge of the Minkowski spacetime using these curvilinear coordinates over here. And each of these word lines is a constantly accelerating observer. Just that each one of them will have different acceleration that will diverge as we get close to here. Now you see that this structure will look very, very similar to probably another diagram that you've seen in spacetime, which is the Kruskal coordinates in Schwarzschild spacetime. And in that case, you also have some similar diagram where you have the singularity here, you have the event horizon, and then you have like constant radius coordinates that look something like hyperbolas here, right? This is not a coincidence because this guy over here is also an horizon, because this portion of spacetime is completely causally disconnected to whatever happens here. Because if I have like a photon emitted here, this will go all the way to null infinity and will never enter this wedge. Okay, this is called the Rindler horizon. And indeed, if you basically compute the near horizon limit of Schwarzschild metric, and you do one more convenient coordinate transformation, you can recast the Schwarzschild metric exactly in the same form as Rindler, associating, of course, this acceleration parameter to some property of the black, which is the surface gravity of the horizon. So if you look at the metric here in this new coordinate, so Minkowski metric will look something like this. So yeah, so you see that this is becoming singular when we get to the horizon, basically, pretty much as Schwarzschild coordinates. All right, so this is cool, but this is not exactly what we want to have to solve Klein-Gordon equation, because we can do one final step, that is redefining the spatial coordinate in a more nice way. So we can define the coordinates, the new coordinates chi of psi. Now I don't remember by heart the Fourier transformation. I remember the result though. And actually just write it correctly. So this new chi is defined to be 1 over a natural log of 1 plus ca. So now the range of the coordinates for the new chi is basically that chi belongs to minus infinity to plus infinity, and then tau is untouched. But these coordinates are still covering just this wedge, nothing changes. But now if you write down the metric in this du tau and chi coordinates, this has a really nice form, which is the following. This is just a conformal transformation from just standard Minkowski metric in inertial frame to this guy. So that's very easy, and that's very nice because the Klein-Gordon equation is conformal invariant. So, okay, so let's cancel something, maybe a little bit here. So we've said that Klein-Gordon equation can be written as this way on curved spacetime. Now this is a covariant divergence, so we can write it with the usual formula of 1 over square root of minus g, and then d alpha of the square root of minus g of d alpha phi. Now we can compute this guy pretty easily because that's basically this guy. When we calculate the determinant of the metric, this doesn't matter, 0 out. So we have d alpha e to the 2yk, and now we can lower this index so we can get out a metric here, g alpha beta, d beta phi, and this guy is just e to the minus a chi eta alpha beta, or eta alpha beta is just the Minkowski metric in inertial frame. So these two guys simplify, and so we are left exactly with box equals 0. I'm gonna put a prime here because this box is expressing the tau and chi coordinates, which are not the same as t and x. This is important. But this is cool because now I immediately know what is the basis v of my solutions for the accelerating frame. This is pretty nice. So my v basis in terms of tau and chi will be just e to the I, let's call it big omega just to distinguish, of tau, and then e to the I k tilde chi. So this is with the complex conjugate, we have a full basis, a complete set of solutions for the Klein-Gordon equation in the Rindler coordinates. Now, I just want to mention one thing that might be deceiving here. So we said before for the two inertial observers that we share the same functional form from the solutions. But here is a bit trickier because the coordinate transformation now from tau and chi to t and x is non-linear now. It's no longer like the proper Tartnus easy transformation. So we cannot recast the coordinate transformation of the coordinates into the wave modes anymore. So this is much more complicated actually when you want to relate the v's and the u's of the inertial frame. And this indeed will lead to the Bogoliubov coefficients not vanishing. Okay, so how much time is left?
Around 5 or 6 minutes.
Okay, so I won't probably have time to go fully into the details of the rest of the calculation because it's pretty long. But if you are interested, I will post my notes so you can just check them or just knock on my office and we can discuss about it. But the idea is just what I said before. So you expand the field only in the right Rindler wedge. In this case, you expand it in terms of the basis of Minkowski spacetime, you expand it in terms of the basis of Rindler, and then you basically project the equations to get out the Bogoliubov coefficients. The only thing that you have to be careful is that the basis that we derived here, it's complete only on the right Rindler wedge. So it does not cover the entire spacetime. So you cannot express basically the basis of the inertial frame in terms of just those solutions. To do that, you extend this basis to the entire spacetime. So also to the left wedge, which is actually easy because these coordinates can cover with a slight modification also the left wedge, and also the upper and lower. So this is done by some analytical continuations. You can do that. In the other case, you can still always express these guys in terms of the inertial base, because the inertial base cover everywhere in spacetime. And this is actually what I'm doing on my notes. But these are two equivalent ways of tackling the same thing, the same calculation. What we will get out of it is basically that this guy, it's going to be, I want to put the 2 pi correct. What you will get is that, okay, so in principle you will get a divergent, like a UV divergence here. That's fine, that's just QFT in action. But let's assume this is a finite volume and we are all fine. But then on the denominator we get actually the nice part. And we basically get something like this. Let's see, yes. So some of you probably all of you might recognize what this guy is. This is Bose-Einstein distribution. If I define a temperature looking at this guy, that is basically, sorry, without this guy. Okay, maybe the KB should be up. No, it's up. Okay, so this is the Unruh temperature. Okay, so we see that this scales linearly with acceleration. And just to give you an idea of why this thing rises, basically, so the sign of this guy, it's coming from the commutation relationship that we set, bosonic commutation relationship. If you have quantized, let's say, a Dirac field with anti-commutation rules, we can basically recover the same result we did last year. So, which is Fermi-Dirac statistics. Then this, like, where the exponential is coming from is basically coming from these guys, so by the shape of the coordinates themselves. But this is the result. So we have a temperature, like this guy sees a thermal bath for each mode omega, which is just K basically, and it sees this temperature. Now if, very last thing that I want to cover, if one, now look at like Schwarzschild spacetime for example, and does this near horizon limit of the metric, you can basically recast it in this form and can read off the acceleration. Now, I don't know if I have time to do that. It's not super complicated, but let's see. So you start from the Schwarzschild metric. And then so on. So you can do common denominator here. Now in the near horizon limit, so if the horizon are at 2m, you can basically say this is roughly 2m. So this is now almost, so near the horizon. And so you can basically recast this piece into some new coordinates, let's call it ρ. And so now you see that we are getting to Rindler's form, right? So you can invert this thing and you can get basically the ρ in terms of the r. And if you do that, you will get some like 8m, and then we get square root of r minus 2m. And if you plug in this inside here, what you get out is basically that your Schwarzschild metric will look something like 1 over 16m squared, dt squared, minus ρ squared, and then the rest. So this piece over here is exactly that form. I mean, you can shift if you want this ρ thing here. Sorry, I think I missed the piece. Yes, there is a ρ squared, of course, here. So you can shift this ρ if you want, like this, and then you are truly in exactly that form. So you have 1 plus 1 over 4 times ρ squared dt squared minus d ρ squared, and so on. So you can read off that the acceleration is this 1 over 4m, which is the surface gravity of the horizon. So if you plug in this guy into here, into the Unruh temperature, what you get is 1 over 8 pi kb. And if you get back all the units that we have ditched from the very beginning, then you will get more ugly expression. See, so you will get at the top an h bar, then you have c cubed, and then finally a g, sorry, I forgot an m as well here. And this is Hawking radiation. So the idea is that physically, you can interpret Hawking's radiation as Unruh radiation in the sense that I have like a local inertial observer that is like falling in the black hole and he sees the vacuum. But if I'm hovering above the horizon, I have some rockets that are pushing me out of the pool of gravity, so I'm accelerating with respect to free-falling observers. And so I no longer see the vacuum, but I see a thermal state. And this thermal state is Unruh radiation. It can be interpreted in this way. Now, all the interpretation of like particle creation and the pair creation that like one particle goes out of the horizon and one gets sucked in, can also be in sort of sense interpreted in this Rindler picture, but it's a bit less formal in a way, so you have to be a bit more careful. But it still can be done, because at the end, what we did here was basically tracing out the full Minkowski vacuum just by considering this right Rindler wedge. So in a way, you can basically show that the full Minkowski vacuum is an entangled state of both the left and right Rindler wedges, in a way. So when you're just considering this wedge, you're basically tracing out the left part of the decomposition of the field. So you're left basically with a partial view, which is a thermal state. So you're like teaching some information out of your system. So you're left with some ignorance, some thermal radiation. So yeah, this is it. I think that no more time. Any questions?
we might have to leave questions
Yeah.
for Guido after, but yeah, thank you. This was fantastic.
Yeah, thanks so much.
Hope it was understandable.
It was.
Pretty good.